Hello. Hello. Welcome to my setup. This is my OBS, as you can see. Right, so what we will be doing today is I wanted to try to see if I could go through the Godot documentation, maybe use it to try to learn how to make some games. Now, if you didn't know, the Godot engine is a sort of game framework. It has the engine, lets you use a type of, I guess it would be called a domain-specific language, which is basically just a language that is used in a really specific context, called GD script. It's a language similar to Python. And what you can do with this is that you can make games. So, this was actually kind of rough to set up, showing my entire screen, because it's OBS is kind of weird about laptops like mine that have both integrated and dedicated graphics cards. So I needed to force OBS to use my integrated card in order to capture my whole screen. So it's possible that will lead to some problems. I honestly don't know. I've never done it before. But hopefully it will be fine. We'll be able to get through this unscathed. Right, so on my browser, I have the documentation open right here. Going to zoom in a lot. Phew, perfect. Okay, so now we've got this on sort of mobile mode. We'll be able to get started here. Okay. So, this sort of goes over the interface. So the project manager is what we were looking at here. This is where we're going to manage our projects. Has an asset library with a bunch of templates and little things to help you get started. And we're going to create a new project. Actually, I'll just use this one that I have set up. Test. Okay. So if we scroll down here, look at the editor, we've got a viewport in the middle, inspector here, our playtest buttons, workspaces, the main menu, the scene, the file system. Here's all the consoles. Okay. Right, so this is all stuff that's kind of technical. I kind of want something that will go through making the game. Okay, here we go. Your first game. Perfect. This tutorial will guide you through making your first Godot project. Okay, let's save this. Save it right in here. And there's my WinRAR. And we can just extract that like that. We'll want to copy it. Okay, so now we want to go to our project and project settings, and under display window, we set to 480 by 720. 480 by 720. And for stretch, set mode to 2D, aspect to keep. In this project, we will make 3 independent scenes, player, mob, and hood, which we will combine into the game's main scene. In a larger project, it might be useful to create folders to hold the various scenes and their scripts, but for this relatively small game, you can save your scenes and scripts in the project's root folder, identified by res. You can see your project folders in the file system dock in the lower left corner. Okay, so I believe we should be able to open this and paste. And that'll give us our dodge assets. Okay, perfect. So the first scene will define the player object. One of the benefits of creating a separate player scene is that we can test it separately, even before we've created other parts of the game. Node structure. To begin, we need to choose a root node for the player object. As a general rule, a scene's root node should reflect the object's desired functionality, what the object is. Click the Other Node button and add an Area 2D node to the scene. Okay. So we need an Area 2D node. You can see right here. So, with Area 2D, we can detect objects that overlap or run into the player. Change the node's name to player by double-clicking on it. Okay, so we've got our node here. We double-click on it, and we can change its name to player. Okay. Now that we've set the scene's root node, we can add additional nodes to give it more functionality. Before we add any children to the player node, we want to make sure we don't accidentally move or resize them by clicking on them. Select the node and click the icon to the right of the lock. Its tooltip says, make sure the object's children are not selectable. Okay. So this is what we want to click. Locks those in place. So now we save. Okay, so for this project, we will be following the Godot naming conventions. GD script, classes, nodes, use Pascal case. Variables and functions use snake case. And constants use all caps. Right, so if you don't know, these are just different sort of syntactic formats, ways of naming things in programming. Pascal case is when you have the words capitalized and sort of mushed together. Snake case is when you have the words in a name separated by an underscore, while each separate word is not capitalized. And all caps is just what it looks like. It's all caps. So, briefly, in programming terms, a class... I should go over variables and functions first. Okay, so a variable is basically a label you put on a set of data, and you use that label to refer to that data. And this can store numbers, it can store sequences of letters that are called strings, and it can store what are called objects. Functions are like, if you've ever done abstract math, there's the concept of functions there, whereas you have a set of data, you feed that set of data into a function, and then it will give you back a modified or different set of data. That's sort of the general idea of functions in programming too. You have an input, you give a function a bunch of data, and you have an output. The data the function returns gives back. And what happens inside the function is the function. And you can sort of treat it like a black box if somebody else made the function, as long as you know that it works properly. But you can make your own function to read, modify, change, and sort, manipulate, filter. You can do all sorts of things with data, and a function will change things. And a class represents a sort of blueprint that you can make entities called objects with. An object is a bunch of properties and functions that sort of represent a scope. It will be easier to explain this stuff once I actually get into it, but that's the basics of what all this stuff is saying. So Godot gives you some options. You can either use the built-in GD script, which is a sort of Python-like language if you've ever used Python before, or you can use C#, which is a sort of modernized C language variant. It's starting to get more common in game development. C languages has always been very commonly used for games, especially C++, because C++ introduced a sort of object-oriented approach. But C# is getting more popular specifically because of XNA and Unity. XNA was sort of the library for game development that was basically made for Xbox, carried over to PC as well. And Unity is another game engine, and probably one of the most popular ones, especially for indie developers right now. Right, so let's move on. Sprite Animation. Click on the player node and add an animated sprite node as a child. The animated sprite will handle the appearance and animations for our player. Notice that there is a warning symbol next to the node. An animated sprite requires a sprite frames resource, which is a list of the animations it can display. To create one, find the frames property in the inspector and click empty new sprite frames. Click again to open the sprite frames panel. Okay, let's start doing this. Create a animated sprite node. Right, so frames property, new sprite frames, and then we get this down here, like this here. On the left is a list of animations. Click the default one and rename it to walk. Then click the new animation button to create a second animation named up. Find the player images in the File System tab. They're in the art folder you unzipped earlier. Drag the two images for each animation, named Player Gray Up 1 and Player Gray Walk 1, into the animation frame side of the panel for the corresponding animation. Okay. So for up, we drag these two. And for walk, we drag these two. The player images are a bit too large for the game window, so we need to scale them down. Click on the animated sprite node and set the scale property to 0.5, 0.5. You can find it in the inspector under the Node 2D heading. So we have these. Finally, add a collision shape 2D as a child of player. This will determine the player's hitbox, or the bounds of its collision area. For this character, a capsule shape 2D node gives the best fit. So next to shape in the inspector, click empty new capsule shape 2D. Using the two size handles, resize the shape to cover the sprite. Let's center this guy here. And what we want is a collision shape 2D. And we give that a capsule shape. And we drag this. Until we've got a nice shape around the player object. There we go. When you're finished, your player scene should look like this. Yep, that does. Okay. So, now we need to add some functionality that we can't get from a built-in node. So we'll add a script. Click the player node and click the attach script button. Okay. I think what I want to do is increase this font size. There we go, perfect. You can guess what a lot of the other stuff around here is for as I'm talking about it, but it's important that you guys can see this code. Okay, so we'll start by declaring the member variables this object will need. Now, the member variables are sort of like the properties or the attributes of a class. A class instance holds its own copy of the member variable that is separate from all other instances of the class. So, for example, if you have two player objects in the world, one of them can have, say, 400 speed, and the other would be able to have 200 speed. And they wouldn't need to be connected in order for each player to manage themselves. So, player speed equals 400. It's a habit. In a lot of other languages, you need to end lines with a semicolon, but not in GD script. And we'll need a screen size too. Okay, so one of the things I know and I can tell you about is that the export word here means that this variable following the keyword will show up in the UI, and you can modify it within the UI here. So I can show you. If we go back to our player here, you'll see. Actually, let me change this too. Okay, I'm going to restart this quick. because I want this to have slightly I want this editor to have slightly larger text. Okay. There we go. Now let's open the player scene again. Here we go. That's a little more readable for you guys. You can see here, under script variables, we have a speed that's set to 400 by default, as we said in the script. Yeah, it's explaining it right here. Using the export keyword on the first variable speed allows us to set its value in the inspector. This can be handy for values that you want to be able to adjust, like a node's built-in properties. Click on the player node and you'll see the property now appears in the script variables section of the inspector. Remember, if you change the value here, it will override the value written in the script. This doesn't apply to us. Okay. The ready function is called when a node enters a scene tree, which is a good time to find the size of the game window. So, this is the ready function. A node will always have one, either implicit or defined like it is here. And it's called when the node enters the scene tree for the first time, as it says in the comment here. So what we want to do here is set this variable up here. We declared it up here. You can see it. We want to say set this variable to the size of the viewport rect. Now these are both functions. What's happening here is that first this function is called get viewport rect. This is a global function that will allow you to retrieve the rectangle that the viewport uses in order to draw to the screen. So that's the window for the game. And when it has that data, what it do is it runs another function that this data has called size, and that retrieves the size of the area. So what this is saying is, for my screen size, please retrieve the viewport rectangle and give me that rectangle size. So that's how we're getting the screen size here. Now we can use the process function to define what the player will do. Process is called every frame, so we'll use it to update elements of our game, which we expect will change often. For the player, we need to do the following: check for input, move in the given direction, and play the appropriate animation. Right, so this is your basic update loop. Games are typically structured based on several loops. You have a update loop and you have a draw loop. Sometimes a game will combine them, but they're usually done very separately. The update loop will handle the inner game logic, like the variables, the objects, things like that. And the draw loop handles rendering that all to the window. So with that separated, you can have stuff going on in the background that you don't necessarily draw. And you can prevent a lot of issues with frames per second that way. If you don't know, frames per second is the sort of measure of how many frames occur each given second. And that's usually handled by the draw loop. If the frames per second runs faster or slower than how the game operates, you can hold the whole thing up. So that's why the loops are typically separated. I don't know if I explained that right. Let me think. Okay, so you have the draw and update loops, but if you combine them both into one loop, you can end up with some problems because things will be drawn faster or slower than they're actually updating. So you can end up hitching up the game. If you separate those loops, you can go at a steady frame rate. There we go, I think that explains it right. Alright, so first we need to check for input. Is the player pressing a key? For this game, we have 4 directional inputs to check. Input actions are defined in project settings under Input Map. Here you can define custom events and assign different keys, mouse events, or other inputs to them. For this demo, we will use the default events that are assigned to the arrow keys on the keyboard. You can detect whether a key is pressed using input is action pressed, which returns true if it's pressed or false if it isn't. Okay, so we have our input, and we'll show you what this is doing. Hold up. Oh, that's not a function. My mistake, that is a member variable. Okay, so we can uncomment this since we're using it. And this is the process function. The delta is sort of represents the difference between this and the last, the difference in time that has occurred between this and the last time the process was run. So this delta is crucial in making sure that your program runs at the right speed, because you feed that delta into your movement and it keeps things moving at the right pace. Nope. Get out of there. Okay, so the process is run every frame, and what we want to do first is declare a movement vector. So a vector is just an X and a Y. That is all that a vector is. It can be used in a lot of different ways, but fundamentally, It's just two sets of data, an X value and a Y value. Here, we're using it to represent what direction the player is moving. So, let's define this. And that will define our vector. And we check each key. So here we have the global input object, and we request its function. We call its function is action pressed UI right, which is the default keybind for the right arrow key. Okay, once I'm done with this, we can briefly talk about what this is doing. Okay, so you might be wondering what this if means. It's a simple conditional statement. It's a piece of logic that says if the thing to the right is true, then do the things here. So in this case, I'm asking, hey, input object, is the action pressed UI underscore right? If that function returns true, so it would look like that, then this will be run. If not, this will not be run. So, that is the basic rundown of how a conditional works. It's a logical statement, and it functions logically. Right, so what we're doing here is we're removing the indent that's here. If we de-indent, it means we're done with this block of code, and we're moving on to a different conditional. Okay, so what is this block of code doing so far? Well, if the right arrow, specifically, if the input representing the action UI right is pressed, which is the right arrow button, our velocity is equal to 1. We add +1 to our velocity for x, rather. If the action for left is pressed, we remove 1 from the velocity x. If the UI down input is pressed, we add 1 to the y velocity. And if the up button is pressed, we remove 1 from the y velocity. Okay, so okay, now what's this block of code doing? So I'll let the tutorial explain it. So we start by setting the velocity to 0, 0. By default, the player should not be moving. Then we check each input and add or subtract from the velocity to obtain a total direction. For example, if you hold right and down at the same time, the resulting velocity vector will be 1, 1. In this case, since we're adding a horizontal and a vertical movement, the player would move faster diagonally than if it just moved horizontally. We can prevent that if we normalize the velocity, which means we set its length to 1, then multiply by the desired speed. This means no more fast diagonal moving. Right, so and with the sprite stuff, we also check whether the player is moving so we can call play or stop on the animated sprite. The $ symbol is shorthand for get node. So in the code above, animated sprite.play is the same as get node animated sprite.play. Right, so if we go back to this animated sprite, that's right here. That's what we added to the player before. That is this. It goes whoop, 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 whoop. So that's where that's coming from. In GDScript, the $ symbol returns the node at the relative path from the current node, or returns null if the node is not found. Since animated sprite is a child of the current node, we can use animated sprite. Now that we have a movement direction, we can update the player's position. We can also use clamp to prevent it from leaving the screen. Clamping a value means restricting it to a given range. Add the following to the bottom of the process function. Make sure it's not indented under the else. So let's do this. We'll separate it a little bit for readability. So we multiply the velocity by the delta. This is a vector multiplication, so it applies to both the x and the y. And what this does is it sort of keeps the speed of everything constant, so that, like, not every frame in not every frame in the game's code will run at exactly the same speed. So what delta does is it allows us to, regardless of how long it takes each time for the function to run, the frames will always occur at the same rate. So this helps us to keep the speed of everything constant at the rate that we want. Position X. We will clamp. That between 0 and the screen size is X. Well, for Y, we will do the same for the screen size Y. Now, what is this doing? So, we are saying that I want the position of this object, the X position, to clamp to 0 and screen size X. So, if my position X is, say, -1, what this will do is say, that's not within our clamp range, let's set that to 0. Same thing goes if it's higher than the screen size X. It will become screen size dot the value of screen size dot X. Same is happening with Y here. So that's just a handy way to keep values within certain bounds. Okay, here's a better way to explain it than I can manage. The delta parameter in the process function refers to the frame length, the amount of time that the previous frame took to complete. Using this value ensures that your movement will remain consistent even if the frame rate changes. There we go. That's how I wanted to explain it. Okay, so we can click play scene, and we can confirm that we can move the player around. First, I need to set the main scene to the player. And this way. As we can see, we have movement. We can move our little guy around. And if we go to the edge here, we can't go past it. We go to the edge here, can't go past it. Go to the edge up here, can't go past it. And down here, can't go past it. So we're stuck in these bounds. That's what all the clamping is for. So we've got our little guy moving. There's going to be little notifications for other people's streams on the bottom. That's alright. Okay, choosing animations. Now that the player can move, we need to change which animation the animated sprite is playing based on its direction. We have the walk animation, which shows the player walking to the right. This animation should be flipped horizontally using the flip H property for left movement. We also have the up animation, which should be flipped vertically with flip V for downward movement. Let's place this code at the end of the process function. Okay. So we go back into our script. Make a new section of code. If our x velocity is not 0, which means it's probably 1, we want our animated sprite animation to be walk. So we don't want it flipped vertically. And what I like to do with these is I like to put them in parentheses, because that makes it more explicit that I'm taking the value of that. But anyways, what this is doing is, so looking at the animated sprite, I want my flip horizontally to equal the value of this. This is a comparison, so if the velocity x is less than 0, this will essentially be true. If it's not, it will be false. So what this is doing is it's assigning it to the value of an expression. So if the y velocity is not equal to 0, we want the animation to be up. And we have a similar thing here. If the velocity y is greater than 0, then this will be true. Otherwise, it would be false. Okay, so this explains it a little bit. The Boolean assignments in the code above are a common shorthand for programmers. Since we're doing a comparison test, Boolean, and also assigning a Boolean value, we can do both at the same time. Consider this code versus the one-line Boolean assignment above. Yeah, so basically it's another way to do what would otherwise be a much messier branching conditional. So, going back to this quick. This is an else if. In GDScript, it's elif. Slightly weird, but not unheard of. So basically what that is it's sort of a continuation of the if conditional. So this is going, if velocity x is not equal to 0, then do this. However, if velocity x is not equal to 0 is false, if this is not true, then it moves on to here and says otherwise, if velocity y is not equal to 0, do this. And there's also a third that we've seen up here called else. And this runs if this conditional is not true. If none of the conditionals in a sort of chain are true, then the else's run. So if we have an else if here that was true, this else would not be run. However, if the else if was also false, then the else would be run, if that makes sense. Okay, so play the scene again and check that the animations are correct in each of the directions. So as you can see, our guy is moving around now. And he's got little animations. They're very simple, but they work. When you're sure the movement is working correctly, add this line to ready so the player will be hidden when the game starts. We know it's working properly, so we can add this to ready. Okay, so next we're moving on to preparing for collisions. Now, we want player to detect when it's hit by an enemy, but we haven't made any enemies yet. That's okay because we're going to use Godot's signal functionality to make it work. Add the following at the top of the script after extends area 2D. Signal hit. So, this defines a custom signal called hit that we will have our player send out when it collides with an enemy. We will use area 2D to detect the collision. Select the player node and click the node tab next to the inspector tab to see the list of signals that the player can emit. So as we can see, this is the signal that we just defined. Notice our custom hit signal is there as well. Since our enemies are going to be rigid body 2D nodes, we want the body entered body node signal. This signal will be emitted when a body contacts the player. Click to connect and the connect a signal window appears. We don't need to change any of these settings, so click connect again. Godot will automatically create a function in your player's script. Okay, so we need to connect to body entered. And that gives us a new function to work with. On player body entered. And this will be run when the signal on player body entered is emitted. So the player will hide after being hit, and we will emit the signal that we have. Alright. So, each time an enemy hits the player, the signal is going to be emitted. We need to disable the player's collision so that we don't trigger the hit signal more than once. So that's what we're doing here. Disabling the area's collision shape can cause an error if it happens in the middle of the engine's collision processing. Using set deferred tells Godot to wait to disable the shape until it's safe to do so. This is very useful. So it will do this as soon as possible, but only when it's safe. The last piece is to add a function we can call to reset the player when starting a new game. So, I'm gonna have all the event-based stuff on the bottom, so I'm going to place this function above it. This is our function. It will set the position of this object to this, which is the argument, the data that is sent to this function. And we show the player. And we enable the collision. Awesome. So that's our player so far. Now we can move on to the enemy. Now it's time to make the enemies our player will have to dodge. Their behavior will not be very complex. Mobs will spawn randomly at the edge of the screen, choose a random direction, and move in a straight line. We'll create a mob scene, which we can then instance to create any number of independent mobs in the game. So instancing is simply the idea that you have a class, which is a blueprint for objects, and you have a lot of different instances of this class running around. Each of these instances has their own set of member variables and functions. And these instances are crucially independent from each other. Okay, so let's get our enemy set up. We want scene, new scene. We want the base to be a rigid body 2D. We name it mob. Let's give this an animated sprite. A collision. Shape 2D. And a visibility notifier. We will set the children to not be selectable. In the rigid body 2D properties, set gravity scale to 0. That's in the inspector here. The gravity scale is 0. So it does not fall. Under the physics body 2D section, we want to uncheck the first box of the mass property. And what this will do is it makes sure that these mobs do not collide with each other. They can go right through each other. Set up the animated sprite like you did for the player. This time we have free animations: fly, swim, and walk. There are 2 images for each animation in the art folder. Adjust the speed FPS to free for all animations. Okay, so fly, swim, walk. So we say fly, swim, and walk. We set all of these to free speed. And we grab our art. Flying, swimming, and walking. And we set playing to on here. And as you can see, that gives us a little preview of what that will look like. We'll select one of these animations randomly so that the mods will have some variety. Like the player images, these mob images need to be scaled down. Set the animated sprite scale property to 0.75, 0.75. There we are. As in the player scene, add a capsule shape 2D for the collision. To align the shape with the image, you need to set the rotation degrees property to 90. Give that a capsule shape. And under transform, we want 90 degrees. We get that to roughly take the shape of our mob. There we are. That's good. A little bit thinner. There we go. So we'll save what we've got so far. And now we add the script. So we want a min speed and a max speed. When we spawn a mob, we'll pick a random value between min speed and max speed for how fast each mob will move. It would be boring if they were all moving at the same speed. Now, let's look at the rest of the script. In Ready, we randomly chose one of the free animation types. Okay. So we have a bear called mob types. And for that, we want the animated sprite, frames, get animation names. And this will give us a collection of all the animation names. Now we set our animation to a random integer that is modulo the size of this collection of animations, so it would be free for us. So modulo is kind of a pretty magic sort of I don't know how to explain it. Like, the modulo is the remainder that you'd get if you divided the left-hand side by the right-hand side. So it has a lot of really interesting applications in math. You can use it to do a lot of cool things. In this case, what it's doing is it's sort of binding the possible results of this expression to between 0 and the size of mob types, which would be free. So with this, we would get a random number in between 0 and free. Not including free, mind. So that's an interesting thing Modulo can do. First, we get the list of animation names from the animated sprites frames property. This returns an array containing all free animation names. Now, what an array is it's simply a collection of data. In most languages, it's of a specific type, but I believe in Godot they can be any type. You can have anything in these arrays. It doesn't really matter. In this case, we have free strings. Strings being a collection of letters, like a word, a couple of words, a paragraph, even just a single character if you want. That's basically what a string is. It's just textual data. We then need to pick a random number between 0 and 2 to select one of the names from the list. Array indices start at 0. That's a big thing. That trips up people who are just starting programming. Arrays almost always start at 0. The only exception I can think of is the language Lua, in which they start at 1. This is because Lua was designed specifically with people who don't program in mind. So they decided that while it was mathematically inconsistent, it was more important that people would be able to intuitively understand where a list of data starts. So they said, we're going to make this one. Arrays start at 1 for Lua, even though they start at 0 for pretty much everyone else. So that doesn't really apply to what we're doing here, but it's an interesting little fact. So, as I said, randi modulo n selects a random integer between 0 and n minus 1. So in our case, it's 0 and 2. And note here, you must use randomize if you want your sequence of random numbers to be different every time you run the scene. We're going to use randomize in our main scene, so we won't need it here. That's important. This is how random seeds generally work. You need to get the seed going before you can have truly random numbers. Well, about as random as a computer can handle anyways. True randomness is kind of a platonic ideal nobody can really reach. Anyways, the last piece is to make the mobs delete themselves when they leave the screen. Connect the screen exited signal of the visibility notifier 2D node and add this code. Okay, so we go back to our object here, go into node for the visibility notifier, and on screen exited, we connect this to our mob, and we get this function here. And on that, we can run the queue_free function. I believe this... Yeah, so what queue_free does is it queues the object to be deleted, but only when it's safe to do so. So as soon as it's safe to destroy the object, it gets destroyed. Alright, now we're on to the main scene. Now it's time to bring it all together. Create a new scene and add a node named main. Ensure you create a node, not a node 2D. So, like that. Click the instance button and select your saved player.tuxum. So that's this, instance a scene file as a node. That will put our player on the scene. Now, add the following nodes as children of main, and name them as shown. Values are in seconds. A timer named mob timer. A timer named score timer. A timer named start timer. And a position 2D named start position that indicates the player's start position. Okay. Set the wait time property of each of the timer nodes as followed. For mob timer 0.5. So in the wait time over here, at 0.5. On the score timer, I set that to 1. It's already 1. And start timer should be set to 2. Okay. In addition, set the one-shot property of start timer to on. And set position of the start position node to 240, 450. So it will be right down here. Spawning mobs. The main node will be spawning new mobs, and we want them to appear at a random location on the edge of the screen. Add a path2D node named mobpath as a child of main. When you select path2D, you will see some new buttons at the top of the editor. Select the middle one, add point, and draw the path by clicking to add the points at the corners shown. To have the point snap to the grid, make sure Use Grid Snap and Use Snap are both selected. These options can be found to the left of the lock button, appearing as a magnet next to some dots and intersecting lines respectively. So these things. Like that. Draw the path in clockwise order, or your mouse will start pointing outwards instead of inwards. 1, 2, 3, 4, 5. Okay. Alright, so we've got our path set up. Now that the path is defined, add a path follow 2D node as a child of mob path and name it mob spawn location. This node will automatically rotate and follow the path as it moves, so we can use it to select a random position and direction along the path. Your scene should look like this. Yep, sure does. Main script. Add a script to main. At the top of the script, we use export packed scene to allow us to choose the mob scene we want to instance. Okay. Add our script. We have our score variable. And under ready, we want to randomize, which will set our random seed. Click the main node, and you will see the mob property in the inspector under script variables. You can assign this property's value in two ways. Drag mob from the file system panel and drop it in the mob property. Or click the down arrow next to empty and choose load and select mob. We are going to drag it. Here we go. Next, select the player node in the scene dock and access the node dock on the sidebar. Make sure to have the Signals tab selected in the node dock. You should see a list of signals for the player node. Find and double-click the hit signal in the list. This will open the signal connection dialog. We want to make a new function called Game Over, which will handle what needs to happen when a game ends. Type Game Over in the receiver method box at the bottom of the signal connection dialog and click Connect. Add the following code to the new function, as well as a new game function that will set everything up for a new game. Okay, so on a game over, the score timer is stopped and the mob timer is stopped. Well, on a new game, the score is initialized, set to 0. The player starts at their start position, which is this right here, the position we set there. And the start timer is started. Now connect the timeout signal of each of the timer nodes to the main script. Start timer will start the other two timers, and score timer will increment the score by 1. So we'll do the mob timer later. Connect these now. Okay. So this means when these timers time out based on the wait time that we set before, right here, these functions will run. On mob timer timeout, we will create a mob instance, pick a random starting location along the path 2D, and set the mob in motion. The path follow 2D node will automatically rotate as it follows the path. So we will use that to select the mob's direction as well as its position. Note that a new instance must be added to the scene using add child. Okay, so we choose a random location that's within the path 2D. We create a mob instance. Then we add that mob as a child. That will make a mob object underneath the main node. We set the mob's direction. This, I assume, is the constant for pi. That will give us a direction. Now we set the position. To the mob spawn location. And we add some direction, some randomness to the direction. And set the mob's rotation to the direction we've messed with. And we set the velocity, which is the speed and the direction. So rand range is exactly what it sounds like, random number within a range. Then we rotate that velocity along the direction we've set. So, this is some slightly complicated math stuff. Basically, what you need to know is that it sets the position and the direction. So, why pi? In functions requiring angles, GDScript uses radians, not degrees. If you're more comfortable working with degrees, you'll need to use the dig to rad and rad to deg functions. Okay. Okay, so let's test the scene to make sure everything's working. This to ready, new game. And we need to assign main as the main scene. Don't think we've saved it yet. So we need to do that, and then we can set the main scene to main. Save everything. And let's see if it works. Yep. Burp. We got squids moving around. And the collision's already working, so when we collide with one of them, we die. And we're dead forever. Okay. So now that we're done testing, we remove this. And the final piece our game needs is a UI, an interface to display things like score, a game over message, and a restart button. Create a new scene and add a canvas layer node named HUD. Canvas layer, and we call it HUD. HUD stands for Heads Up Display, an informational display that appears as an overlay on top of the game view. The canvas layer node lets us draw our UI elements on a layer above the rest of the game so that the information it displays isn't covered up by any game elements like the player or mobs. The HUD needs to display the following information: score, changed by a score timer, a message such as game over or get ready, and a start button to begin the game. The basic node for UI elements is control. To create our UI, we'll use two types of control nodes, label and button. Create the following as children of the HUD node: a label named score label, a label named message, a button named start button, and a timer named message timer. Here we are. Click on the score label and type a number into the text field in the inspector. The default font for control nodes is small and doesn't scale well. There is a font file included in the game assets called seleniumregular.tiff. So first, let's try that out for ourselves. So if we go into text, and right here, it's very small, as you can see. So under custom fonts, choose new dynamic font. Click the dynamic font, and under font data, choose load and select the Selenium regular file. You must also set the font size. So we want that to be 64. And that gets bigger to accommodate that. And now, if we add text, it looks much larger. Once you've done this on the score label, you can click the down arrow next to the dynamic font property and choose copy, then paste it in the same place on the other two control nodes. Okay, we can do that. Copy that on the other two nodes. We paste our font. Okay, we have a note here, anchors and margins. Control nodes have a position and a size, but they also have anchors and margins. Anchors define the origin, the reference point for the edges of the node. Margins update automatically when you move or resize a control node. They represent the distance from the control node's edges to its anchor. Range the nodes as shown before. Click the Layout button to set a control node's layout. You can drag the nodes to place them manually, or for more precise placement, use the following settings. Score label. Layout, top wide. Text 0, align center. So, for score label, we say top wide. We set the text to 0, and we set align to center. For message, we set the layout to H center wide. That puts it down there. We set text to dodge the creeps. We set align to center. And we set the auto wrap to on. For the start button, we set the text to start. We set the layout to center bottom. And we set the margins top -200 and bottom -100. And on the message timer, we set the wait time to 2 and set the one-shot property to on. Now, we add a script to HUD. With a signal start game. Signal tart game. The start game signal tells the main node that the button has been pressed. Oops. There we go. We make a function, show message. Makes the messages text the given text, shows the message, and starts the message timer. It's called when we want to display a message temporarily, such as get ready. And we have another function, show game over, which will use that function. And we yield for the So what this will do is it will block everything until the message timer runs out. Then it will run the stuff below. Wait. Actually, what I want to do... There we go. That's how it's supposed to be. And go back to our script. Now we show the message. We make a one-shot timer. The getTree function gets our node tree. So we can create stuff under it. This dynamically creates a little timer, and it waits for that timer to time out. And when it does, we show the start button. This function is called when the player loses. It will show game over for 2 seconds, then return to the title screen, and after a brief pause, show the start button. When you need to pause for a brief time, an alternative to using a timer node is to use the scene tree's create timer function. This can be very useful to add delays such as in the above code, where we want to wait for some time before showing the start button. Okay, and now create another function. And what this will do is it will set the score to a string representation of the score. Connect the timeout signal of message timer and the press signal of start button and add the following code to the new functions. Okay, so we go to the message timer, node signals, timeout connect. And we do a similar thing to this, the press signal. Alright, so start button. When it's pressed, we hide the button and we emit the signal that says, hey, we need to start the game now. And on the message timer timeout, all we need to do is hide the message. Okay, so now that we're done creating the HUD scene, go back to main. So, got our main scene. Instance the HUD scene in the main like you did the player scene. The scene tree should look like this. Hold on. There we go. Save that. Right to main. And we instance our HUD. There we go. Now we need to connect the HUD functionality to our main script. This requires a few additions to the main scene. In the Node tab, connect the HUD start game signal to the new game function of the main node by typing new game in the receiver method in the connect a signal window. Okay. That should connect to our new game. If we click there, we see the connection. Source HUD, signal start game, target is main. That's exactly what we want. In new game, update the score display and show the get ready message. Update with our score. And we show a message. Get ready. In game over, we need to call the corresponding HUD function. And finally, add this to on-score timer timeout to keep the display in sync with the changing score. Now you're ready to play. Okay. So, let's save everything. And if we play, we've got the score up here, we've got a message here, and we've got a button. Burp, burp. So if we start, hold up. Aha. Got some bug splatting to do. Invalid call to function update score in base canvas layer HUD. Expected 1 arguments. Uh-huh. Duh. Okay. This is bug fixing. Now it's working. Now we get a game over. And the game resets properly. Okay. That's working pretty well. Hold on. Okay, there we go. Need to make sure my stream manager is going, because that's the only way I can know what's going on with the stream. Okay, so back to what we were doing. Removing old creeps. If you play until game over and then start a new game right away, the creeps from the previous game may still be on the screen. It would be better if they all disappeared at the start of a new game. We just need a way to tell all the mobs to remove themselves. We can do this with the group feature. In the mob scene, select the root node and click the node tab next to the inspector, the same place where you find the node signals. Next to signals, click groups and you can type a new group name and click add. So if we go into mob and groups, we can add a group. called mobs. Now all mobs will be in the mobs group. We can then add the following line to the game over function in main. Get tree, call group, mobs u3. So this will call the queue_free function on everything that's in the mobs group. And our mobs will always be in the mobs group because we have added that here. So every mob that still exists will be deleted as soon as it's safe to do so. We've now completed all the functionality for our game. Below are some remaining steps to add a bit more juice to improve the game experience. Background. The default gray background is not very appealing, so let's change its color. One way to do this is to use a color rect node. Make it the first node under main so that it will be drawn behind the other nodes. Color rect only has one property, color. Choose a color you like and select layout full rect so that it covers the screen. Okay, let's do that. So in our main, let's save this first. In our main, we can add a color rect. And we can select a color for it. Let's do something really obnoxious. It to that. Correct. And now we've got an eye-searing magenta background. Make this a little less obnoxious. There we go. We want that to be the first node under main. Okay. That's the background. Sound effects. Sound and music can be the single most effective way to add appeal to the game experience. In your game assets folder, you have two sound files, houseinaforoustloop.ogg for background music and gameover.wav for when the player loses. Add two audio stream player nodes as children of main, one the music and the other def sound. On each one, click the stream property, select load, and choose the corresponding audio file. To play the music, add music play in the new game function and music stop in the game over function. Finally, add def sound play in the game over function. And something I'm going to do. I'm going to go into these. Okay. Wait. Is that? It shouldn't be like that. Here we go. Save everything. Keyboard shortcut. Since the game is played with keyboard controls, it would be convenient if we could also start the game by pressing a key on the keyboard. We can do this with the shortcut property of the button node. In the HUD scene, select the Start button and find its shortcut property in the inspector. Shortcut, here we go. Select New Shortcut and click on the shortcut item. A second shortcut property will appear. Select New Input Event Action. And click the new Input Event Action. Finally, in the action property, type the name UI Select. This is the default input event associated with the spacebar. Now when the Start button appears, you can either click it or press space to start the game. Okay, that's this tutorial. So, let's figure out if our little improvements have worked. Going to press the spacebar here. And we've got some music. And if we die, get the game over sound. So, it's a very simple game, but everything's working. We've got a player, we've got enemies, we've got a score based on the amount of time you survive. Everything you need for a really basic rudimentary game, but it works. Okay, so at this point, going to give my thoughts, what I think about this so far. Okay, so I really like what I've done with this engine. Seems to sort of have the right mindset for like what people want when they're developing a game. Like the node system, it took a little while for me to really fully understand it, but now that I do, it makes a lot of intuitive sense. GD scripting seems really easy to get a handle on. I was able to understand like 90% of what was going on here. this math down here got a little dicey. But that's probably the only thing in this entire project where I didn't 100% understand what was going on. So it's a very intuitive language. You can tell that it's based on Python. Works really well. And one of the things I like a lot here is the built-in assumptions regarding signals. Like, a lot of games are extremely event driven, and it helps a lot to be able to separate what things are doing and have your objects communicate through these signals. So, like, the, say, timers don't need to know what anything else is doing. All they do is they set a timer, they repeat if they're set to, and they emit a signal every time the timer goes off, and that signal can be sent to other things like it is here. This timer sends a signal to this function. This function runs. It doesn't have to know the timer exists otherwise. It just runs when it's called. And I think that's really good. It's exactly what you want when you're developing games. You want your concerns to exist independently. You don't want things becoming super dependent on each other, and I think an event system like this really helps a lot with that. Everything was very easy to do. And yeah, I can imagine using this a lot in the future. Seems easy, but it seems really powerful too. So, I'm going to quickly see if there's maybe one more tutorial I can go through. So, here's a UI design tutorial. Okay, so it's a follow-up on an earlier one. Design a title screen. In the next two tutorials, you will build 2 responsive UI scenes step by step using the engine's UI system. The main menu, and a game UI with a health bar, energy bar, bomb, and money counters. You will learn how to design game UIs efficiently and how to use Godot's control nodes. This page focuses on the visual part, everything you do from the editor. Learn how to code a life bar. Read Control the Game's UI with Code. Okay. I'll do the first one of these. And then, after I'm done with this, I think I'll call it quits for tonight. So, let's download the project files. We'll stick that in documents. And then we need to restart Godot. and import our project. That will be under, what was it? UI main menu design, that's right. It'll be under U. Start project. Okay, so we have a set of assets and the icon. And otherwise, we're working from a blank slate. To design a good UI, you want to come up with a rough mock-up first, a plain drawing version that focuses on the placement of your UI components, their size, and user interaction. Pen and paper is all you need. You shouldn't use fancy and final graphics at this stage. Then, you only need simple placeholder sprites and you're good to jump into Godot. You want to make sure the players can find their way around the interface using those placeholders. So to give a little example here, placeholder doesn't have to mean ugly, but you should keep your graphics simple and clean. Avoid special effects, animation, and detailed illustration before you have players playtest your UI. Otherwise, the graphics might skew the player's perception of the experience and you'll miss out on valuable feedback. If the user experience doesn't work, you'll have to redo some sprites. Tip: always try to make the interface work with simple text and boxes first. It's easy to replace the textures later. Professional UX designers often work with plain outlines and boxes in grayscale. When you take colors and fancy visuals away, it's a lot easier to size and place UI elements properly. It helps you refine the design foundation you'll build upon. Okay, so there are two ways to design your UI in Godot. You can build it all in a single scene and eventually save some branches as reusable scenes, or build template scenes for reusable components and create specific components that inherit from your base scenes. We'll use the first approach because the first version of your UI may not work as well as you'd like. You're likely to throw parts away and redesign components as you go. When you're sure everything works, it's easy to make some parts reusable, as you'll see below. Before we jump into the editor, we want to plan how we'll nest containers based on our mockup image. Here are my 3 rules of thumb to find the right containers. Break down the UI into nested boxes, from the largest that contains everything to the smallest ones that encompass one widget, like a bar with its label, a panel, or a button. If there's some padding around an area, use a margin container. If the elements are arranged in rows or columns, use an H-box container or V-box container. These rules are enough to get us started and work well for simple interfaces. For the main menu, the largest box is the entire game window. There's padding between the edges of the window and the first components. This should be a margin container. Then the screen is split into 2 columns, so we'll use an H-box container. In the left column, we'll manage the rows with a V-box container. And in the right column, we'll center the illustration with a center container. Containers adapt to the window's resolution and width to height ratio. Although we could place UI elements by hand, containers are faster, more precise, and responsive. This tutorial is based on a window size of 1366 by 768. So, let's change that Under our window, we want to make sure these are the right numbers. Yep. Let's create the main menu. We'll build it in a single scene. To create an empty scene, click on Scene, New Scene. We have to add a root node before we can save the scene. Your UI's root node should be the outermost container or element. In this case, it's a margin container. Margin container is a good starting point for most interfaces, as you often need padding around the UI. Okay, so we add a root node that's a margin container. We name it main menu. Select the margin container again and head to the inspector to define the margin size. Scroll down to the control class to the custom constant section. Unfold it, set the margins as such. 120, 80, 120, 80. Twenty 80, 120, 80. We want the container to fit the window. In the toolbar above the viewport, open the layout menu and select the last option, full rect. So we want layout, full rect. And we've got a full rectangle there. Select the margin container and create the UI elements as texture rect nodes. We need the titler logo, the free text options as individual nodes, the version note, and the main menu's illustration. Click the Add Node button and texture rect. Okay. So we want texture recs. And we want 5 of them. There you got 5 texture recs. Oh, okay. So that would be 6 texture recs, I think. Click each of the nodes to select it. In the inspector, find the texture property and click Empty Load. A file browser opens and lets you pick a sprite to load into the texture slot. Repeat the operation for all texture rect nodes. You should have the logo, the illustration, the free menu options, and the version note, each as separate node. Then, double-click on each of the nodes in the Scene tab to rename them. Nothing has been placed in containers yet, so they should look messy. Okay. So we want to get textures for all of these. Characters. The second will be the continue label. The third will be the new game label. The fourth will be the options label. The fifth will be the title. And the sixth will be the version. Okay. Our main menu has some margin around the edges of the screen. It is split in two parts. On the left, you have the logo and the menu options. On the right, you have the characters. We can use one of the two containers to achieve this, H-split container or H-box container. Split containers split the area into two, a left and a right side, or a top and a bottom side. They also allow the user to resize the left and right areas using an interactive bar. On the other hand, HBox Container just splits itself into as many columns as it has children. Although you can deactivate the split container's resize behavior, I recommend to favor box containers. Select the margin container and add an HBox container. Let's add that. HBox container. Then we need two containers as children of our HBox container. A VBox container for the menu options on the left, and a center container for the illustration on the right. So we add a VBox container and a center container. In the node tree, select all the texture rect nodes that should go on the left side, the logo, the menu options, and the version node. Drag and drop them into the VBox container. The node should position automatically. So we got the title, continue, new game, options, and version. And the others, and this should go in the center container. We're left with two problems to solve. The characters on the right aren't centered. There's no space between the logo and the other UI elements. To center the characters on the right, first select the center container. Then, in the inspector, scroll down to the size flags category and click on the field to the right of the vertical property and check expand in addition to fill. Okay, so we go to the center container, go to the size flags category, and expand both ways. This makes the center container expand into all available space while respecting its neighbor VBox container. Finally, drag and drop the characters node into the center container. The characters element will center automatically. We just did that. To space out the menu options and the logo on the left, we'll use one final container and its size flags. Select the VBox container and add a new node inside it. Add a second VBox container and name it menu options. So we name that menu options. And we select all three menu options, continue new game and options. And put them inside menu options. Now that we grouped the menu options together, we can tell their container to expand to take as much vertical space as possible. Select the menu options node. In the inspector, scroll down to the size flags category. Click on the field to the right of the vertical property and check expand in addition to fill. The container expands to take all the available vertical space while respecting its neighbors, the logo and version elements. To center the nodes in the VBox container, scroll to the top of the inspector and change the alignment property to center. To wrap things up, let's add some separation between the menu options. Expand the custom constants category below size flags. And click the field next to the separation parameter. Set it to 30. Once you press enter, the separation property becomes active and Godot adds 30 pixels between menu options. Yeah. Nifty. Without a single line of code, we have a precise and responsive main menu. Alright, so that's pretty neat. So UI has a so the Godot UI seems to be very web inspired. It uses a lot of the same properties as CSS, cascading style sheets. How that interacts with the DOM of a web page. So that's pretty neat. Kind of like how easy it is to make something that will look good. Because a lot of UI systems aren't very good in game engines and such. I think the last time I tried using Unity, its user interface stuff was just horrendous, like terrible. I'm sure there's custom things people have rolled out, custom assets that are better UI frameworks than the Unity's defaults. But when I used it, it was just awful. This, by comparison, is pretty fantastic. Yeah. So, I've spent about 2.5 hours on this. And would I return to doing this? Absolutely. I had a fun time, like, getting all this stuff working. I got something online very quickly and enjoyed doing it. I think it's a good engine. Seems underutilized, which is surprising to me. Seems pretty robust. It's more robust than a lot of things that already have a lot of games for them, you know? But I guess with this application in constant development, maybe people are kind of anxious to get started doing something when the editor might change drastically in the future. But I think it would be backwards compatible with their projects, so I don't think that anxiety is necessarily founded. So, I'm kind of surprised that there aren't more games out for that were built in Godot, because it honestly seems like it's ready for that. It seems like it's ready for like a big project to be made in it. I don't know. I think maybe I will continue trying it, see if I run into any walls that like would prevent me from using it effectively. Because I don't see anything at the moment that would prohibit a decent sized project from being made in this, but I don't know, you don't really know that until you have like a ton of assets, you have a big sprawling project, and things just stop working. And maybe you're having a hard time debugging stuff. But I don't know. I think it's a solid engine. Probably pretty underrated, lives in the shadow of Unity. And the Unreal Engine. But I think that's gonna do great stuff. I've heard that its 3D is being worked on. It's not quite on par with stuff like Unity and Unreal, but it works. Could be better, but it works. And its 2D is supposed to be really good. So my rating for Godot engine is 5 acting classes out of 6. Seems like a good engine. Seems like it has pretty much everything you'd need to make a good game. There might be difficulties in doing larger projects. I haven't run into that because I've just started using this thing. But my conclusion is that yes, I will be using this to attempt to make a game. And I think it will probably be on the easy side for a game engine. We'll see. But I think I'm done working with this for tonight. Getting a little bit tired. So I think I will quit for tonight. And on Friday, I will be starting a game of Tales of Berseria. It's one of my favorite Tales games, and I've been wanting to play it again. So I'll be streaming it. But for tonight, goodbye, and you will get to see infinity once again as I end the stream. Woo! Woo! Okay. Have a great night or rest of the day, whatever applies to you. And thank you for watching. Goodbye.